All right, differentiability. We hinted at differentiability yesterday. We hinted at it when we talked about left and right hand derivatives. So we talked about the fact that that one piecewise that was like x squared and then 2x wasn't differentiable at x equals 0. But we didn't go into why isn't it differentiable at x equals 0. And that's what we're going to do today. We're going to talk about why aren't functions differentiable at all points in their domain. And essentially we have 3 big reasons. So, a function will not have a derivative at a point P where the slope of the secant line has the following occur. It fails to approach the limit as x approaches a. When will this occur? Well, this will occur if we have a corner. So if the graph has a corner. Anybody know what type of graph would have a corner?
Square.
No. Square isn't a graph, it's a shape. Yes. Absolute value. Exactly. So you're making it with your hands. He's saying the words a V. A cusp.
I have no idea what that is.
A cusp is like x to the 2/3. That's the ones that look like the birds or like the.
They're like the.
I
know.
Yeah,
I know.
cartoon.
They go like this. Whee!
Yeah.
They look like the bee, the birds.
Yeah.
McDonald's.
You guys are so like animated. I should teach you there's like the Macarena with like graphing like lines.
That would ruin it.
I would forget how to graph.
How do you figure out Macarena?
So we hinted at it when in Noah's number 7 there was a vertical tangent, aka an asymptote,
Hey, I had these.
and he's got 1 and 11.
You know, just trying to get my
Recognition.
yeah. Thanks, Glenn.
There also cannot be a derivative, or it will fail to have a slope of the secant if there's discontinuity. So that's why the continuity test is so important.
So, if any of those things are things,
If any of these 4 occur, then the graph does not have a derivative at that occurrence. It doesn't mean it doesn't have a derivative. It just means it doesn't have a derivative at that particular occurrence. So this graph would be differentiable on its domain except at the tip of the
at wherever
the bird feet.
Yeah.
Yes. So let's look at example number 1. That's an absolute value. That is an example of a corner. So you can give yourself a rough little sketch on your paper. Think about, or I could show you why this would fail. What would the limit as h approaches 0 from the left of the absolute value of x be? Or x, sorry. I don't know why I read
Would it
it.
be
Oh.
0? Because
Yeah,
it's just go infinitely close to.
Yeah.
When you looked at me all crazy, but I got scared.
Sorry. The limit from the right would also be,
0.
okay, so the limit is 0. What happens to the slope of the secant then? Is the slope of this line positive or negative? Negative. So remember, differentiability isn't talking about the limit, it's talking about the slope of the secant. So if you found the slope of the secant from the left, so now we're talking, in this slide, I kind of jumped again. The limit is h approaches 0 for f of x plus h minus f of x all over h. The slope of the secant, or the slope of the derivative, would be -1. And you could plug in 2 points if you really wanted to figure that out. Because you could plug in like here and here and find the slope of the secant. Like the slope of the secant would just be picking 2 points. So for example, I could say when x is -2 and h is 1, and you would find the slope between those 2 points. What would the slope of this side of the absolute value be? Yeah, just normal point slope, right? So the limit or the slope of the tangent from the right would be +1. Does the limit from the left equal the limit from the right for the slopes? No. Therefore, it's not differentiable. That's the difference. The limit can exist. We're talking about the limits for the slopes not existing for differentiability.
Okay.
Does that make sense? Like, do you see the difference even between the two of these?
Do we have to check the limit of the actual function?
No. I just wanted to show you the difference.
So it's just always
This is the limits we care about for differentiability. So this is just a normal limit. This is differentiability.
Is it the same thing as DNA?
No.
But just slope.
Okay? Example, f of x equals x to the 2/3. This is your cusp or your berm, where the slopes of the secant line approach infinity from one side and negative infinity from the other. So again, like what that's saying is like the limit as x approaches a of f of x plus a minus f of x for this one is going to the infinities. Okay? X to the 1/3 is a vertical tangent. The vertical tangent is slightly different than a vertical asymptote. A vertical tangent doesn't break continuity, but it has like this straight up and down aspect to the function. Okay, and then example 4, that is jump discontinuity. So that is a piecewise function. So again, jump discontinuity or any discontinuity is not differentiable. Infinite, removable, or jump. This is just an example of jump. Pascal.
Clean
Did you get blocked for that fundraiser? That's so cool. So then what do you have to do with the flamingos after you get blocked?
I'm going to sit in the back of my truck right now. So they are.
Yeah, you just give them.
Do you give them back to like the school?
Yeah.
Is that Mrs.
Somebody else
Bashmore
is
who's in charge of that? That's cool.
I was going to do that by rollerblades.
Alright, so let's look at an example. It says find all the points in the domain of this function where f is not differentiable. So this is again just going back and knowing how to graph. What does the positive 3 tell us here? Good. What does the negative 2 inside tell you?
Right.
So this graph is shifted right 2 and up 3. What's the slope of this absolute value? Yeah. So on an absolute value, where would the point of discontinuity be? Yeah. Yeah. So, perfect. That would be at 2, 3. So the function will not be differentiable at what x value? Yeah. Differentiability is not bad, right?
So far.
Good.
This is gonna be.
It's not.
We're gonna throw in some
Yeah.
cosines and tangents.
So that leads to a theorem. And the theorem is kind of like, I always give this theorem to be the example like a square. All squares are rectangles, right? But not all rectangles are squares. So if f has a derivative at x equals a, then f is continuous at x equals a. So this is like saying, if it is a square, then it's a rectangle. You cannot say if something's a rectangle, though it's a square, right?
You can't say that it's continuous.
Well, you can't say that something is differentiable just because it's continuous. It's the reverse of that. Like this is saying because it's differentiable, it is continuous.
You can't say because it's different.
Because it's continuous, it's
Oh,
differentiable.
that's what I meant.
Continuity does not imply differentiability. That's the idea. And that's why I think like this little, like, it is important to recognize the converse is not true, and that a continuous function might not be differentiable. I will tend to say continuity does not imply differentiability. I think it's much easier and much more concise. Continuity does not imply differentiability. Think of an example of a continuous function that is not always differentiable. What function has a domain of all reals but isn't differentiable everywhere?
Oh.
What was the question?
Absolute values, the cusps, right? All of them have domains of all reals, but are they differentiable everywhere? No. So this cusp is totally continuous. You trace your fingers, right? If you find the limit from the left and the limit from the right, does it always equal the same value?
Yeah.
Oh.
And then is that value going to be the value of the limit? So it's continuous by the continuity laws, but it's not differentiable. So continuity does not imply differentiability. Remember that intermediate value theorem we had? How would you explain the intermediate value theorem real quick?
That like there's a point and a point up here and a point down here, and there has to be some point C in the middle that has.
Perfect.
Yeah, if it's
So if you have a closed interval from A to B, wherever it starts and wherever it ends, there has to be a point that exists between the middle. That one made me sad on your multiple choice. Because like we didn't read them like carefully. Like you didn't match the X to the X, the Y to the Y. So again, it says if A and B are any 2 points in the interval on which the function is differentiable, then f prime takes on every value between f prime of A and f prime of B. So again, what that means is like if your derivative lives between A and f prime of A, and here's B, I'll put f prime of B in the negative just for the heck of it. So it means that there is some C in the middle of these where f prime of C would be any y value between them. Because we know this function has to go, doesn't matter if it looks like this. It has to go from A to B and be connected. It could be a line. It could be just a little hump. Oh, it's gotta go back down. We don't really know what it looks like, but we know that C exists, and so does f prime of C. Where f prime of C lives anywhere between f prime of A and f prime of B. So some of my favorite questions then become, at what point in the domain does this function appear to be differentiable, continuous but not differentiable, or neither? So so differentiable would be an interval up 2 points. So this graph would start at 0 and be differentiable until the jump, which is 1. From 1 to 2. Because what happens at 2? You have a corner, right? And a jump. But the corner is almost more important. It's not differentiable. 1 would be included here because it'd be continuous. But it's not differentiable at 1.
Why would it be at 0 if the graph locked it up?
Because it's an endpoint of the entire interval. So interval endpoints can be, but not in-er points. So for an endpoint, you assume that it is continuous, differentiable, and pretty from the opposite side. Or that's that whole left-right-hand derivative aspect. Okay, where's my next interval? From 2 to 3. And 3 to 4. Where is it continuous but not differentiable? It's not continuous at 2 though.
So it'd be 2.
You could also, like I was just thinking, like at x equals 3. But yeah, like you could say 2 to 4 or at x equals 3. Yeah, this interval wouldn't even really matter because you just are saying we're like continuous but not differentiable. Where is it neither continuous nor differentiable? At 2 and 1. Because it's not continuous here either. It has jump discontinuity. Okay, I don't want to do the end deriv stuff, so we're going to do the calculator stuff tomorrow. Let me That should be okay. I'm gonna check it real quick. Because I feel like that I cut off. We can do the odds so you guys can check them.
For a second, I thought of that question. And I can see it.
So we're doing all of those numbers.
Just the odds.
Oh, 1 through 5.
That's what I'm checking right now to like see like how much math goes into each one.
I like math games, but I don't like regular math.
Let's only go
Regular math.
1 to 15. And then
15 long.
1 to 15 odds. I'm just going to cut off the last couple.
Is that it?
You can do the 31 to 35. They're more, the 31 to 35 are more like, they're not mathy. There was a lot of math in here. 1 to 30, 31 to 35 are, talk about domains and ranges. So like, when would be, yeah, I know. Like, when would something have an error?
Just 2 and 4.
So 1 to 15 and 31 to 35.